Welcome to today's ABC-UTC Research Seminar. These seminars were previously known as graduate student seminars and were initiated by the ABC-UTC last year as part of its workforce development focus area. They have now been broadened to include presentations by the research principal investigators in addition to the graduate students. The presentations in these seminars highlight research work of the ABC-UTC's consortium universities. In the new format, each seminar consists of a 40 to 45-minute presentation followed by a 15-minute Q&A session. My name is Mary Lou Rawls, Director of Technology Transfer at the ABC-UTC. I will be coordinating today's seminar and will be assisted by Ben Bierman with the FHWA, who will moderate the Q&A session, and Masa Forzad, Ph.D. candidate at Florida International University, who will manage the web room. We're pleased to welcome participants at approximately 600 registered sites for today's web seminar. Today's seminar features the ABC-UTC Phase 2 Experimental Research Project at Florida International University on extending the application of simple for dead load and continuous for live load, or SDCL, to high seismic regions. We're pleased to introduce our presenters, Atorod Azizinamini, Director of the ABC-UTC and Professor and Chair of the Civil and Environmental Engineering Department at Florida International University, and Amir Sadeghnejad, Ph.D. candidate in the Civil and Environmental Engineering Department at Florida International University. Dr. Azizinamini?
All right. Thank you, Mary Lou, and thanks for the opportunity to share with you results of the work that we are conducting. I will explain what the SDCL system is. The SDCL system has been used in the non-seismic areas, and the objective of this project that is funded by ABC-UTC is to extend the system to high seismic areas. In the non-seismic areas application, the system has proven to be economical, and but we didn't have any detailing or a design provision to extend this to the seismic area, so that's why we undertook this project. The lead PhD students on this project is Amir Sadeghnejad, who will be co-presenting with me. The presentation is going to be, I will give you a very brief background on how this system is used in the non-seismic areas, because that's a foundation really you need in order to extend it to the seismic areas. After that, Amir will elaborate on the results of some of the experimental tests, and especially focusing on the experimental tests. He's going to briefly show the results, and then at the very end, I will come back and then share with you some of the conclusions that we have. I also should mention that this is a joint project between the FIU and University of Nevada, Reno, and I will elaborate how we are collaborating between the two universities. For those of you who have not been introduced to the simple for dead load and continuous for live load steel bridge system, typically, the steel bridge system is continuous for dead load and live load. Typically, you have a middle piece. If you can see my mouse, you put a middle piece over the pier, and then you have a other end unit that is bolted to the middle piece that is supported by a separate crane over the pier. So there's a bolted splices. There is a unit, usually need two cranes for the construction or the temporary towers, things like that. In this system, you just place the girders, steel girders, between the supports, and then you place some reinforcement over the middle pier, and then you cast the deck. So when you cast the deck, when the wet concrete is applied to the system, each girder is acting like a simple span. That's where the name simple for dead load comes in. But when the concrete is hardened, then the system becomes continuous for the live load. So therefore, the name simple for dead load and continuous for live loads. Uh, very simply, just to show you, in a conventional system, the dead load, if you put a dead load, let's say the weight of the wet concrete, the dead load also introduces a negative moment, and live load also introduces a negative moment. So in a typical steel multi-span steel bridge, the negative moment is usually higher than the positive moment. That's why in a typical continuous steel girder bridge, we have a heavy section over the pier and relatively lighter section over the positive region. In the case of the simple for dead load, the dead load does not introduce any negative moment. As a consequence, your negative moment decreases somewhat, but the positive moment increases. That has many advantages. The main advantage is that because positive moment is increasing, negative moment is decreasing. Now the same section that works in a positive section most likely is going to work in the negative section. So in this system, you see a photo of a steel bridge that was constructed using a SDCL. The positive moment increases and the negative moment decreases. You don't have any bolted connection. That's a lot of saving. Also, when you have a bolted connection, those are an attraction to corrosion problem because you put the girders over the support. You don't need to have two cranes on site. You just need one crane. It's very stable because I'm going to show you the way to achieve the continuity is by connecting the steel girders over the middle support. And during the construction, anytime you have the end of your steel girders secured against the rotation, you have a very stable system. Nothing bad is going to happen during the construction. Those of you who have experience, if anything bad wants to happen, especially with the steel bridge, happens during the construction. And usually those are related to the end support condition. So in that sense, this is a very stable system. Also, service life. We have many problems with the steel girder bridges at the supports because of the water, moisture getting from the top, from the joints, from the expansion joints and so on, and causing a corrosion at the end of the steel girders. In this case, the end of the steel girders are secured against the moisture by being casted inside the concrete. And that helps a lot. So it also, this detail helps the service life. There are other details to achieve this SDCL, the continuity. We do not recommend that. We feel like attaching them using a concrete is a better way to go. So over the pier, really what you need deck. This gives you basically the mechanism to take the tensile force over the pier for negative moment. You also need a mechanism to transfer the compression force. If you use the concrete diaphragm to join the girder, the most important design detailing is to make sure that you have a continuous path to transfer the compression force from one flange to another flange without relying on a concrete. That's very important. Now, you can achieve this using different methods. I will show you one detail that we have used in practice. The detail I'm going to show you have been researched for more than 7 years. This system, we have researched anywhere from the development to the monitoring and so on. I will give you some references that you can refer to if you need more detailed information. This is a busy schedule. What really the essence of this slide is that saying that you need to have treatment at the end of the steel beam that's going to get embedded in the concrete diaphragm. You need to have an end plate, and you also need to have some mechanism to transfer the compression from one flange to another flange without going through the concrete. If you do that, then you will get a good behavior. If you don't, For example, here is a one test specimen that we didn't have any end treatment. So there was no end plate. There was no mechanism to transfer the compression from one girder to another girder. And as a result, the bottom flange crushed the concrete and the capacity of the specimen dropped by 50%. So this is the most important thing that you need to follow. Now, one detail that we have used on many projects, by the way, there is many of these bridges in service right now. They have exhibited very nice behavior. One detail is the end of each girder at over here, over the pier. Okay, there's an end plate, and then there's a steel block. The steel block that we have used is as wide as the width of the flange of the girder. It's about 2 inch thick, and the height is about 4 inch. Now there is a similar steel block on the other girder too. Now these steel blocks over the pier, they do not have to touch each other. Some people, they worry about the tolerances and so on. As long as you have some contact or maybe 1 inch gap, you should be fine. There is no need to have these steel blocks of one girder and the other girder to completely touch each other. Just that even a 1 inch probably gap would be just fine. So here is the detail. I hope that you can see that. Basically, over the pier, you see the portion of the girder that is embedded in the concrete diaphragm. Each end has a steel plate, end plate, and then the steel block. These steel blocks, they don't have to be full penetration weld or anything, just tack welded, because you're only transferring the compression. This is another shot on a one job. Again, in this case, you have some contact, but again, you don't, even if you have a, let's say, ½ inch or so gap between the steel block, you would be just fine. This is another shot of the same bridge. Okay, you can see that steel block over here, end plate, and the steel girder. This is the concrete diaphragm. The sequence of the casting is that you fill this concrete diaphragm maybe halfway, and then you wait for a couple of days until that concrete is hardened. After the concrete is hardened, then you go ahead and cast the deck and the remaining of the concrete diaphragm. Another thing that's important, you can we have a detail that allows this whole concrete diaphragm over the pier to rotate. So it is hinged using these dowel bars. It behaves like a hinge, so it cannot translate horizontally in either direction, but it can rotate, and that you can put some soft material underneath of that concrete diaphragm between the cap beam and the concrete diaphragm. Now the ABC application, again, this is a non-seismic. In the ABC application, what you have is either steel box or steel beam. You cast the concrete on top of basically the box or the steel beam, and then you bring this unit, you put them side by side, and the longitudinal reinforcement that you need for the live load continuity, you can develop those by hooking them in the concrete diaphragm. And one more thing is that in a typical bridge, we need about 1% longitudinal reinforcement over the pier for steel bridges. For live load continuity, the amount of the longitudinal reinforcement increases to about 2%. The design of that is very simple. It's just like a reinforced concrete beam, and we have a document that tells you how to design, how to size the rebars for continuity. But in a sense, it's about 2%, about 2% of the concrete area. So in the SDCL as applied in non-seismic areas with the ABC application, it is very user-friendly. First of all, this is a SDCL system that uses the steel box. You form it up in the basically on the ground. Now, in this particular job, it was very the contractor, in fact, I was on the job site when they brought the girders. The contractor just put some gravels, put some steel beam, and then the girders were placed over this support that was built in just a matter of less than an hour. And then after that, you form it up, and then you cast each unit. Basically, you can have a partial depth deck, or you can have a full depth. Okay, these are modular units. You can also cast a railing system if you wish. This particular project was 139 feet each span, and the unit, the steel box, with the concrete on the top, even if you go with the full depth deck, it's going to weigh less than 100 tons, which is very appealing. And then once the concrete is hardened, and then you can take each unit and then place them over the supports, and you get this condition right here. So this is a two-span continuous. So we have 1, 2, 3, and then 3 on the other span. Then you close your longitudinal joints, and then over the pier. Now, this particular project used the partial depth, and then they came back and put the 2-inch silica fume-based overlay on top of that to finish the project. Now, one of the advantages that you will have with this system is that because you don't have a creep and shrinkage deflections, and the creep and shrinkage deflection gets more serious as the length of the system, the length of each span increases. And since you don't have the creep and shrinkage deflection, then the elevations tends to match. My recommendation would be that for the longitudinal joints, you would be better off just use a full depth deck. But then, in my opinion, at least, is the use of the UHPC would be much better option. This particular bridge was constructed back in the 2008, 2009, and then there is an archived webinar that you can listen to it by Mark Trainovich of the Nebraska Department of Roads. The detail for this is showing the detail over the pier. As you see over here, we can take the longitudinal bars that about 2% of the concrete area. You can hook them basically and develop them that way over the pier. This is a shot of in the previous slide. Everything is nice in the drawing, but in the practice, things are not as beautiful as the drawings. And in fact, in this particular job, we had some interference. Some of these longitudinal bars that were hooked in the concrete diaphragm, they were hitting each other, but nevertheless, we were able to manage it. That detail has been tested. Now, this is what I was saying, that in order to allow the rotation of the system over the pier, you can put some soft material between the concrete diaphragm and the cap beam. And there are dowel bars that come from the cap beam inside the concrete diaphragm to allow basically this unit, this detail, to act like a pin. It will prevent the translation along the length or in the transverse direction, but will allow the rotation. Each module, again, can be constructed without temporary bracing. The worker safety is ensured. You can have the partial or full depth deck. You can have the railing actually cast before you move the unit into the place. For a span of about 135, in fact, this was 139 feet. With the deck, you're looking at the whole thing to be weighing 100 tons, which is very, very nice. Theoretically, there is no span limitation for using this system, except the only thing that you have to watch out is that with this system, your deadload camber tends to be high. For example, for 139 feet, the deadload camber that was specified was about 12 inches. And when you're looking at the high, very large deadload camber, that can create some challenges So that would be the only consideration. If you need more information on non-seismic application of the SDCL in ABC format, look at the November 7, 2012 archive of our webinar in our website. Very good presentation by Mark Trainovich with Nebraska Department of Road, Assam, and Fuad Jabber. Also, if you need more information, the second and third quarter issue of 2014 of AIC Engineering Journal. Between the second and third quarter issue of 2014 has a 5 journal paper that provide you all the technical information that you need for this system. Okay. Now, then we started this project because we wanted to extend the application of this SDCL to the high seismic areas. The detail that we used, as you saw in the previous slides, the steel blocks in the bottom, they were, you can show that almost all the time they are just transfer the compressive force. But in the case of the seismic, because of the moment reversal, there's a good possibility that you will get the bottom flange subjected to a tensile forces. So you need some mechanism to take the tensile forces in the bottom flange. So that's why we had to do additional research in order to extend the system into the seismic areas. Now, there are several different systems for seismic that actually allows. For example, in Alaska, they like to isolate the superstructure from the substructures. California likes to have a frame action, so the substructure and superstructure is integrated. In the seismic design, you need to make sure that the joint areas remains elastic and all the nonlinearity or the plastic hinges take place at the end of the columns. So we selected the type of the practice that the California prefers. So this is we approach the problem in a way that trying to develop the system so that the substructure and the superstructure act as a frame. Now, in order to understand what type of forces the connection that is going to experience during the seismic event, okay, we decided numerically to investigate 3 different types of loading. So, there is a good dissertation that provides the logic behind this. If you are interested, we will try to put that dissertation on our website. This loading that we investigated numerically is basically taking a column and two basically portion of the deck subjecting to the moment reversal. This will be simulating the type of the forces that the joint is going to see when the system is subjected to excitation of the traffics. This loading right here that you see is, we said that this is going to tell us what type of forces the joint is going to experience under the vertical excitation. So if you have a seismic event and is going to be subjected to a high vertical excitation, this would have told us, okay, what kind of forces is going to be transferred to the joint. And that is important because you need to design the joints for those forces. And then, of course, this one is for the gravity type loading. So again, there's a good dissertation justifying why we use these 3 type of loading in order to understand what forces the joint is going to see during a major seismic events. Now, out of all that, I won't go through all the details of it. We concluded that under the horizontal excitations, you basically need some vertical rebars. We call them dowel bars. That is coming basically in the that you need to have in the joint area. For vertical excitation, you need these reinforcement, the tie bars, basically to mechanically tie the two girders together. You need that. And then, of course, you need these steel blocks for the gravity type loading. So this is the detail that we have. Now, the nice thing is that the next question is that how much reinforcement do you need? We did very extensive numerical, nonlinear finite element analysis, and we concluded that if we provide all this reinforcement that you see here in the amount that is specified by the Caltran, you would be just fine. So that was good for us, because at the end of the day, we don't have to do lots of research or the experimental or numerical work to see how much reinforcement do we need here. There's already a specification, and if you follow just the Caltran procedures to design the amount of this reinforcement, will be fine. So that was a good news, and that was verified by quite extensive numerical investigation. So how do you apply this system in the seismic areas? Well, you have it using an ABC. You have what you do, first of all, you have your foundation, you put your precast columns, and then you put some precast cap beam. Okay, this is not the full diaphragm depth, just a precast cap beam over the precast columns, and this should be designed to hold the girders that's going to have a deck on top of it. So once you have this, then you put in the ABC application, you put the steel girders that already has a deck on top of it, and then after that you put the concrete here, and then you close the longitudinal joints, and then you complete the bridge. So again, that's the sequence: precast column, and then you put that partial cap beam on top of it. Then you put the girders with the concrete on the top, and then you close it up. Okay. So where are we at with the project? We have developed a detail that you can use the STCL in the seismic areas. The amount of the steel that you need right now, our conclusion is that the Caltran procedure is sufficient to design it. We have the detail that I showed you. We have conducted a component testing, which Amir is going to give you the brief overview of it. After that, University of Nevada, Reno is going to conduct a shake table test with that detail placed in the test specimen to verify. And once we do that, then we should be with about a year, probably I would say a year and a half. We should be able to complete the project and then propose the complete design provisions. In order to for the shake table test and the component testing, the prototype bridge was a 2-span 95-foot, 4-girder, 8-foot 4-inch spacing, 2-lane of traffic, and our test specimen was the distance between the point of inflection in the deck and the point of inflection in the column. And for us, it was easier to take this and make it upside down and test it the upside down, like over here. Okay, here's the test specimen, represents portion of the deck. Okay, so upside down, and then portion of the column, the distance from the face of the cap beam to the point of inflection at the column. Now, the test specimen was subjected to a constant axial load representing the dead load that's going to be there, and a cyclic lateral load. The cap beam was designed based on the Caltran provisions, and so the purpose of the component testing was to verify that when we subject this specimen to the constant axial load at the level of about 10% of the pure axial load capacity of the column, and the cyclic lateral load, the plastic hinge is going to form at the end of at this point, and the cap beam is going to stay completely elastic. So our test specimen, again, is about 19 feet. The distance between the end support to end support is 19 feet. The the height of the column is about 4 foot, 4.5 feet, and I think about 1 foot. The diameter of the column is 1 foot 4 inches, so 16 inches. Okay, so what I'm going to do at this point, I'm going to turn it to Amir, who's going to briefly tell us the results of the component test that was he completed.
Thank you, Dr. Azizinamini. Okay, I will go over further details of the experiment and briefly discuss the results of the component test. For capacity protected members, Caltrans proposes that the superstructure should remain elastic. The inelasticity is then forced to take place at predefined location within the substructure. To make sure that the design superstructure remains elastic, the superstructure capacity needs to exceed the overstrain capacity of the column. As you can see in the figure on the left, the overstrain capacity of the column is calculated, also shown on in the figure on the right, and is compared to the bend cap capacity. You can see the capacity of the bend cap well exceeds the column overstrain capacity. After designing the connection and bend cap based on the required capacity, Caltrans provisions were used for different components of the bend cap and the connection. As Dr. Azizinamini already discussed, we have the details for seismic STCL connection consists of vertical reinforcement, which carries the moment reversal loads, side reinforcement, which goes through the web of the girders. We have tie bars between the compression flanges in order to carry possible tension forces, the bearing blocks, and additional deck reinforcement to carry the negative moment for continuity of the connection. Caltrans provides the design criteria for these horizontal and vertical bars, and the remaining details were designed based on the first phase of the project. So here you can see the perspective view of the test setup. An axial load is applied on the column to replicate the actual structural behavior. The axial load applied is almost 10% of the axial load capacity of the column. The lateral load replicates the longitudinal component of the seismic loads. We carried out the test at FIU Structure Lab. Because of our inverted test design, the sequence of construction is somewhat opposite of how a typical bridge is constructed. We started with the deck, after which the cap beam was casted, and lastly, the column was made. Here are some photographs of the specimen before the casting of concrete. The specimen was sufficiently supported at the bottom to prevent any undue deflection. We used these auxiliary beams in transverse direction to prevent movement of the girders during the concrete casting. We removed the beams later on. These auxiliary beams were used only because of the inverted test setup. This is, however, not needed on the site. Here are some additional photos after the deck was casted. The interface between deck and cap beam was left roughened, so to have a good bond. You can see the details of the reinforcement here in this picture clearly. These are the vertical bars, the tie bars, and the bearing blocks. This photo shows the casting procedure of the cap beam. The cap beam was casted 3 weeks after the first step. We have some additional photos for casting of cap beam. and at the end, the column was casted. So this is the overview of the completed specimen. The auxiliary beams were removed and the supports under the deck were also removed. All components of the specimen were cured and covered with plastic sheets to prevent moisture loss. Next step was preparation of the test setup. The lateral and axial load mechanisms were put in place. You can see here the actuators used for lateral cyclic loads, and we had the hydraulic rams to apply axial loads. The crack formation and propagation was mapped during the entire run of experiment at maximum displacement level in each cycle. This is the area which you're looking at in these pictures. This is the region where the plastic hinge occurs in the column. Loading procedure is shown here. At each displacement level, 3 cycles were applied. The displacement level was increased by 1 delta Y after each 3 cycles. And delta Y is the yield displacement of the column calculated during the first cycle. We observed that the crack initiated in the plastic hinge region, which was followed by cover crushing during the first 3 cycles, and the cover spatting extended to large areas as the displacement level increased. No cracking was observed in the cap beam until 3 delta Y displacement level. However, you can see that a crack initiated on the cap beam. The crack which I showed you in the last slide started to propagate at later stages of the test. Although this was superficial damage, but we believe that better construction practices at larger scale will prevent such damage. Also, Caltrans provision suggests the bend cap width to be at least 2 feet wider than the column diameter, which means 12 inches on each side of the column to the cap beam edge. Since this parameter was scaled down to 4 inches on each side, it is believed that this might be the reason for damage on the cap beam. The mode of failure for experiment was fracture and buckling of rebars. At this stage, we observed that the core concrete of column had crushed extensively. From hysteretic curve, we found that almost 20% strength degradation had occurred, and at the end of the first cycle of 7 delta Y displacement level, the testing was halted. This figure represents the load displacement curve. For each displacement, 3 cycles were run. We observed that there is no substantial strength degradation up to the last cycle. We can see the specimen shows sufficient ductility and symmetric behavior. The results are also compared with moment curvature analysis, the red line. And we see a very good agreement between them. Based on the experimental results, we can conclude that the failure occurred at the first cycle of 7 delta Y by fracturing one of the column longitudinal rebars, and this caused a 20% decrease in the capacity of the column. At this point, the test was terminated. Based on this, the ductility level of the column is concluded to be around 6. The specimen was instrumented with strain gauges on column longitudinal rebars. Results show that the strains in the reinforcement inside the cap beam did not increase substantially. However, the strain gauges on rebars close to the cap beam and column interface showed significant strain on these bars. The strains in plastic hinge region showed an increase as expected. The interface of this Cabin to diaphragm is very important. Therefore, we instrumented the vertical bars with strain gauges to observe the transfer loads. This figure shows the location of the strain gauges on these bars, and this figure shows the measured strain at each level of the test. The results show that the maximum strain occurred near the column. The maximum observed strain in these double bars is almost 800 microstrain, which is much below the steel yield strain. And in this figure, the measured strain in deck longitudinal rebars correspond to the strain gauges location. The strain gauges are located just outside the diaphragm. Due to the symmetrical condition of the slabs, only half of the rebars were instrumented, and the graph shows that the deck remained elastic during the whole experiment. And also you can see in this picture, taken from the bottom of the deck, that the deck remained intact without any appearance of any visible cracking. The curvatures in the plastic hinge locations are shown in this figure for different displacement levels, and the results show good distribution of the curvature along the column. Now I would like to pass the presentation back to Dr. Azizinamini for concluding remarks. Thank you.
All right. Okay. Thank you, Amir, for the summarizing the results of the component test that we did. Okay. So what I would like to do right now is to provide you with some of the preliminary conclusions that we have based on the extensive numerical work and the component test. And as I said, the next step is going to be to learn from all the work that has been completed and then make appropriate changes if it's needed, and then do the shake table test at the University of Nevada, Reno. So one conclusion is that, as the experimental test indicated, is that the connection detail that we have come up with for extending the SDCL to the high seismic areas is working, and in a sense that it made sure that the capacity protected portion of the structure remains elastic. As Amir was mentioned, the maximum strain in the vertical bar in the cap beam was just 800 microstrain. In the deck, we had about 200 microstrain, way below the yield, while the plastic hinge was forming at the end of the column. So in that sense, the connection did its job, kept the cap beam pretty much elastic. And the plastic hinge, of course, formed at the end of the column as we expected. Now, the cracking at the cap beam that you saw, that should not happen, but we believe that's the results of the basically scaling. But we have another detail that actually, if somebody is really concerned about that, we can completely eliminate that. I have some slide that if there's a time I can show you how to do that. Right now, we are continuing to do our nonlinear finite element analysis to even learn more about this system. For example, numerically, this finite element analysis are calibrated with the test. So there are some parameters that we have not studied experimentally. We can do it numerically, such as, for example, the skew effect, things like that. That's going to be continuing. And the shake table test right now is scheduled for November of this year, and we are hoping about a year, probably a year, a little bit longer than 1 year, to have the complete design recommendation. So with that, I'd like to conclude this presentation, and we'll be happy to answer any question that there might be.
Okay. Well, thanks to our presenters today for your excellent presentations. Ben Bierman with FHWA will now moderate the Q&A session. Ben?
Okay, thank you, Mary Lou. Great job, Atorod and Amir. Folks, we received probably, a little over 20 questions here, and I've got them grouped and categorized. in the following, and please send them on in. We've got questions related to the superstructure's performance, questions that are specific to the detail that was being used in the test, questions related to implementation, performance, testing, and installation. So we'll just go ahead and get started. So let's see here, hang on, there we go. Let's see here, with the detail-related questions, simple for dead load and continuous for live load makes sense for pre-stressed beam superstructures due to constructability. For a steel superstructure, what's the benefit of this method comparing the typical steel design of continuous over a pier? It seems that this detail or this strategy has more details involved. I believe, Atorod, you can probably talk about that. You kind of discussed it in the beginning of the presentation there.
Yep. I think actually this the simple for dead load and continuous for live load is a system that has been used for pre-stressed concrete girder bridges for years, and but it has actually more advantages for steel compared to concrete. These are the reasons. Number one, you don't have any bolted connections. You don't have, and that bolted, each bolt by the time of the installation, inspection and all that, it can cost you well over $28, $30 with just one. And you can have 2,000 bolts easily on each span. So the effect of corrosion is gone. And like I said, the other advantage is that because of the change in the moment distribution, you have a section that works in the positive, works in the negative. One of the really, this is more on the conventional side that has a lot of advantage, is that casting sequence is very important, especially in the case of the steel. So if you have a multi-span, you got to cast the positive region and then simultaneously, and then come back and cast the negative region. In the simple and dead and continuous live, if you have a conventional type, you don't worry. You just cast from one end to another because the system is simple for dead loads. The other advantage that I think is a really big item for the steel, the end of the girders are protected against the corrosion. That is a really, I think, the long-term durability, from long-term durability, it's a big advantage. So in my opinion, I think the system has much more advantages for steel compared to the use of the same system for pre-stressed concrete.
Okay. There was a question regarding the testing setup. With the current setup being in the inverted position, how are the simply supported reactions on the drop cap applied? If they were not imposed, would this not affect the test results?
Okay. I think,
and I believe you can go to slide 20. There was a sequence that Amir had shown around 26, 27.
Yep. Right. The test specimen that we had. Let me show you here. Okay. The test specimen. Now we are interested. The point of interest is this right here. This component test was to verify the fact that with this kind of detailing, you're going to have a plastic hinge that forms at the end of the column. And the cap beam was designed based on basically the Caltran requirement. So you're going to have some axial load. So there were rods over here that we applied the axial load, kept it constant. And then after that, we basically applied the cyclic lateral load. Now, this is not as good as if you apply the basically tested the whole system. But nevertheless, we think that it's very good test setup in order to understand the behavior of this region right here. And as you saw, everything else stays completely elastic. So no, I think this setup with the axial load and the lateral load gave us the sufficient information. Now, the shake table test is going to be done up the right way. So we will learn more if there is anything else that might happen in the system from the shake table.
And there was a follow-up to that question too. I'll just slide it in here. Did you also consider the moment due to the weight of the column and loading cap and part of the actuator because of the inverted test setup? If that makes sense. And I believe you just answered it, is because when you go back to the second test, you're going to do everything right side up, I guess, correct?
Yeah, yeah. And the weight of the column and so on is really, it's insignificant compared to the type of the moment and everything else that we applied. If you look at that, it's very minor.
Okay. There's a question. Let's get back into the detail itself. What led the researchers to use the bearing plate detail in lieu of another type of detail, say a bolted flange? Given that there's no shear at the center of the pier, they really don't need to splice up the web. So what was the thought of coming up with the bearing plate detail and the end plate detail?
Yeah, let me show you. I believe the question is related to this
right there
particular detail. Right.
Yep.
This detail.
Yes.
This particular detail really this is the simple as you can go. There are other ways to continue. You can weld a plate to a sole plate, weld it to this flange and the flange of the other girder. Okay, so another way here you can have the you can connect the bottom flanges by bolting a plate and so on. When you do the welding and all that, you get into the fatigue categories. When you're doing the bolting, there are problems in the field. So this one is a very cheap detail. And like I said, you don't have to have a full contact. But the most important thing is that to cast the whole thing in a concrete. There are other details that do not use the concrete to attach the two girders together. In our opinion, that it's not good because you've got too many details that are prone to corrosion. But if you want to cast in a concrete, this is as simple as you can get.
Atorod, we kind of heard perhaps maybe two different things as you all were presenting, just to try to get some clarity here. Around this slide, I believe you had mentioned that there were two closure pores to close up the pier cap. You know, sort of a first and then a second, and I guess the second also included the closure pore of the deck itself. And it looks like in the testing, there was a single closure pore used to make the cap. And I guess the question is leading to, you know, there's cold joints occurring here. So, and then there was also a third mention of using perhaps a flexible material between the pier cap and the closure pore of the pier cap to get additional rotation. Can you kind of clarify between these three different scenarios of
Sure.
what the intent
Sure.
is here? Sure. Okay.
Okay. Now, first of all, the soft material. So there is a concern that when you attach everything with a concrete diaphragm, this whole thing over the pier should be able to rotate, and act as a hinge. So what you do is that you put some soft material. In fact, in the couple of bridges that have been in practice, that's what they have done, like a styrofoam or something they put here, and then they cast the concrete on top of that, and then there's a dowel bar that goes here. Now, that's one question. So as far as how you achieve the rotation. The other question is that, you know, test the specimen, and correctly that was pointed out, is that in our test specimen, we casted basically, we didn't have that cold joint in there. We don't believe that is going to be too important because the moment capacity of this joint right here that you see over here, it is so much higher than the column that should not be an issue. But again, the shake table test, there's going to be a cold joint in the shake table test. So we'll see if there's anything. But I don't believe it's going to be a factor because if you look at this is the overstrength factor, by the overstrength capacity of the column. So you take the capacity of the column multiplied by the overstrength factor, and the capacity of the cap beam is much higher than that. So the cold joint hopefully should not be an issue. But it is correct because of the test specimen, we didn't do a stage casting. We casted this basically, I think, this whole thing in a one shot.
Okay, Atorod, can you go down to slide 34 for the next question? I want to see if we can get a visual here. I believe this is the correct one that will help it. Yeah, and it's kind of specific to the lower right-hand corner rendering that you have there. There was a question related to, I guess it was the uplift, and are those, we'll call them horizontal bars, necessary when you have the vertical dowels and all that's going on to hold the beams and the concrete closure pour in an uplift situation?
Yes, yes, you do. And that, let me show you here. So all the numerical work that we did, it showed that if you have a moment reversal, in fact, these bars are not effective to carry that type of loading. This type of loading, I mean, produces like a tension on this side, it pushes here, and these ties are not effective. So you need only this. Now, on the other hand, when you have this type of loading, like a vertical acceleration, the dowel bar is not effective. And only these bars will become effective. So for under different type of a loading, the different parts of the detail gets activated. So yes, you do need this one. You do need this for the vertical acceleration. You need the vertical bars for the moment reversal. And if we didn't have this, this vertical stereo would not be able to take the vertical acceleration.
And since we're on this question here and looking at this detail, there was a discussion of, how much bearing area is needed with the bearing plates. And early on, you had indicated that it was okay on one detail where they didn't have the bearing plate detail. It was up in the beginning, up further. Right, slide 7. Yes, 7. There it is, right there. Okay, so on the lower right-hand detail, which, yes, that one right there, where we didn't have the bearing plates, you had indicated that there was concrete crushing and it reduced the capacity by 50%. And then further on, with the bearing plate detail, you indicated that a gap was acceptable, maybe up to 1 inch between the end bearing plates. And it seemed kind of counterintuitive of what's going on there. If the idea was to prevent concrete crushing and you're allowing a 1 inch gap between the bearing plates, would that crushing still occur, or should there actually be some kind of contact area between the two bearing plates?
Okay, good question. First of all, if you don't have any treatment at the end of the beam, what happens? You have a very small area of a steel girder that is transferring a large compressive force, and that coupled with the fact that the modulus of elasticity of the steel is 8-9 times more than the concrete, that's why it's going to crush. It's going to crush the concrete, and it's not going to allow the development of the yield capacity of the tension reinforcement. So your moment capacity is going to decrease, and that's why your moment capacity decreases in this case. Now, when you put the end plate, that end plate also helps to distribute the load too. So another way, you don't have all the compressive force being transferred only through the bottom flange, but this end plate also helps. So it's an intermediate solution between this case and full continuity between bottom flange. Now, also related to this, some people say, okay, how about, well, we don't do anything in the case of the pre-stressed concrete girder, so why we don't see that? Well, in the case of the pre-stressed concrete girder, first of all, you have a very large area of a bottom flange that is bearing in the concrete, and the modulus of elasticity of the concrete and the concrete diaphragm is about the same, so you don't have that problem. But in the case of the steel, we will. Now, as far as this gap goes, there has been many of these bridges in service. There have been many of these bridges that have been constructed. And our recommendation is that you need to be, as long as you have maybe about 1 inch or so gap, you don't have to have a full contact. It's a good idea to have a contact here, okay? Like you see here, it's good to have a contact, but even if there was a gap, I wouldn't worry about it because the paste is going to go and fill it up, and it's going to be predominantly compression. Now remember also there's going to be concrete surrounding that, so that concrete is going to be confined. And so you won't have as much problem in that. That's why inch or so is fine. You're not going to get into problem. We don't recommend just to have an end plate with complete gap because that will create a problem because the stiffness at this point, the axial stiffness of the system at this point is much higher than the here. So
okay.
you can't get by just by end plate. You have to have this steel blocks, but if you have about a 1 inch gap, you should be fine.
Great. Okay, where are we at? All right, slide 10. All right, there was a question regarding slide 10. Let's get a visual on that. And then we have to jump to slide 26. Let's see what that slide looks like. There was a question in it basically, are the two details in conflict with one another? Let's see. It seemed like the connection for seismic detail on slide 26 is in conflict with the details shown on slide 10. And what are we looking at?
Okay, here this is seismic application with the ABC. So what you do, you put your precast column, you put this partial cap beam precast, okay, and then you put this detail, but then you have to use the steel reinforcement that using the detail that should go here, the detail that should go here, it should be the same as this right here.
Okay,
so
the bars are spread out. Yeah.
Exactly. So you're going to have this. You're going to have this, okay? And then, let me go back over here. So this way, and then at this point, you're going to have the detail that you're recommending, and then you pour the concrete. So they're not in conflict. No.
Okay, great. It is mentioned that using Caltrans connection detail for concrete diaphragm, is the detail changing based on the seismic design parameters, or do you recommend using the connection detail for the worst case for all applications?
If the question is non-seismic, no, we don't recommend this one for non-seismic at all. That is too much. It's too much. But for the seismic, our recommendation right now is that what's in the Caltrans is good enough, which is based on the I think test that was done at Iowa State actually.
Okay, and a question that sort of complements that is the connection. How would you expect it to behave in regions with very important vertical acceleration components higher than 0.6 G?
That's the purpose of having this right here. In fact, the Caltrans requirement is that to assume 25% of the weight for the vertical. Usually, vertical acceleration is not taken into account. It's not considered regularly. Even in shake table test, that's one of the limitations. The vertical acceleration is not simulated, which I think it's a little bit of a handicap. But if you put these ties, that's why we have these ties right here. Now, we don't have a good design criteria for this right now. I think that's something that we need to work on and establish some criteria based on the numerical method. That's one of the reasons we are doing the parametric study with the nonlinear finite element analysis to study some of the parameters that we were not able to do experimentally. So we don't have it right now. For the component testing, we did some minimal. We put some minimal really reinforcement here, but that needs to be looked into further. If you have a very high, like 0.6 G, I mean, that's vertical acceleration. That would be really high.
Well, and this kind of leads into these next three questions, which really relate to implementation. In the non-seismic simple for dead continuous for live design, is it not currently adopted by AASHTO? And is the ultimate goal for your research to incorporate seismic SDCL into the AASHTO provisions?
I think for non-seismic, really, we are not doing anything different that AASHTO needs to have a specific design provision for it. I mean, we are following everything according to the AASHTO. The only thing that might be required, that some provision should be added to the AASHTO, maybe the maximum, maybe gap between that steel block. Maybe even, I don't believe you need that, but that's the only thing that I can see that should be there. For the seismic, like I said, the fortunate thing was that we did all this study to understand what type of reinforcement do we need in the cap beam in order to resist all the different type of forces that this connection is going to see during the major seismic event, and to stay elastic. And we found out that if you just follow what the Caltrans recommends, then you would be just fine. So there's already a design provisions in the code, so we can just refer it to the Caltrans design provision. So there's no, and beyond that, I think then the question is that maybe to get the Caltrans requirements back in the, I guess, the AASHTO. But the good news is that we are following a code that's already been well accepted by the profession.
And the owner adopted provisions as well as another strategy.
Exactly. Exactly.
And maybe you can elaborate on this, and maybe Caltrans has it or not. Honestly, I don't even know. But have studies been done for bridge applications with moderate to high skews coupled with the moderate or high seismic regions?
To my knowledge, I don't think the skew effect has looked at, but as I mentioned, that's one of the reasons we are doing a parametric study with a calibrated nonlinear finite element analysis to look at the parameters that we have not tested experimentally, and the skew is one of them.
Okay. Well, some more questions related to testing, or in the testing setup. What was the ductility capacity ratio of the lab specimen?
I think Amir was that was 6, right? The maximum displacement ductility that we achieved was 6, and I believe it failed at the first cycle of the 7. Am I correct, Amir? Amir knows the details.
Yes, you're correct.
Okay, and then another question with that was, did you consider the ductility obtained to be satisfactory?
Yes, I mean, you usually need what ductility of 4. Now, another displacement ductility of the 4, I mean, really is what is acceptable. And in this case, I mean, we were way beyond. Well, that's a column. I mean, if you want ductility, you can design your column for whatever you want. The other thing, actually, with respect to displacement, let me just elaborate on this. This is not reflected in the code, but I think in seismic design we need to kind of take that into account. The levels of the level. Let me put over here. The levels of in the test, for example, in a major seismic event, I mean, you are not going to go to this level of needing this level of displacement ductility ratios. And then the other thing that you need to keep in mind is this: the type of the loading that we apply during the test, which is 3 cycles at each displacement ductility ratio, does not really represent any specific earthquakes. So the most common question that somebody could ask is that, okay, so you are telling me to use this system in a seismic event, but then you are testing it using a loading that doesn't represent any earthquake. So how do you justify it? Well, the only answer to that question, that we do this practice in the buildings and the bridges, the only answer to that is this: if you test it, we are subjecting the test specimens to a type of the loading that does not simulate any particular earthquakes. The experience shows that if you subject the test specimen to this type of loading and you survive displacement ductility of 4, 5, or 6, then that detail is going to survive major earthquakes.
So it's envelope the actual earthquake scenario types.
It's not so much enveloping, just another way. This is like a severe test. I want to say, if it survived this type of a loading, then that detail has the capability of surviving a major earthquakes. And if you do a nonlinear time history dynamic analysis, you will see that the loading that any detail such as this experience the seismic event is very complex, and it's if you look at the envelope, it looks like a butterfly. So it's but it is justified if we do that in the building, we do that in the bridge. In the bridge, if you test it and survive this loading scheme, then it's good enough that it's going to survive the major earthquakes.
Okay. Now we're definitely past our 2:10 mark. I want to ask one more question, and that'll wrap us up. And the questions that we didn't answer, we'll go ahead and get those posted. But if we can move on over to slide 49 really quick. Get it up there. Okay. And while that's slide 49, there you go. Is there any reason for using overstrength capacity and the M-phi of the bent camp shown in one of the slides rather than the overstrength capacity of the superstructure? And the reason this is being asked is that designers are interested in the joint behavior of the superstructure performance for the longitudinal in the longitudinal direction. Say it that way. Does that make sense? Okay. If you want me to repeat that, because
could you repeat that? Just make sure that we understand the question.
Yeah. So slide 49. Is there any reason for using an overstrength capacity and the moment phi of the bent cap shown in one of the slides rather than the overstrength capacity of the superstructure? And for whoever posted that, go ahead. I was going to say, whoever posted that, they can more, if they want to add on to that, if I'm not asking it right, go ahead and do so in the Q&A pod.
We are using the overstrength capacity of the column. So anyway, you calculate the plastic moment capacity of the column at the plastic hinge location. You multiply by a factor, and you say my capacity protected element should have the capacity more than that overstrength. So we are using a overstrength capacity based on the column, not. So I think the question maybe they're asking something else.
Right, and not the bent cap. And you're controlling it into the column. That makes sense.
Right.
Okay. Well, folks, we are definitely out of time on that note. And with that, we'll go ahead and pass the baton over to Mary Lou to close this out. Mary Lou?
Thanks. Thanks again to Dr. Azizinamini and Amir for sharing your ABC-UTC FIU research work. Thanks also to Ben for moderating the Q&A session, to Masa for managing the web room, and to all of our participants for your interest and attendance and great questions during the Q&A session. Our next quarterly research seminar will be held on Friday, October the 27th. Details will be posted on the ABC-UTC website as developed. This concludes today's seminar. Thank you.